Alright, welcome back for Chapter 2, Section 2. We are going to talk about equilibrium solutions and stability. So today, we're going to investigate a type of differential equation called an autonomous differential equation. And they basically look like this. You got your first derivative is equal to some function of x. And you'll notice that that function of x does not contain the independent variable. Differential equations of this type can have special solutions called constant solutions. And these, you'll find these solutions at locations called critical points. So what is a critical point? A critical point is a value of x that makes this function equal to 0. So, or a root of f of x. At a critical point, that also makes the derivative equal to 0. So the solution of the derivative, so the solution for the differential equation is equal to a constant. This is why they're called constant solutions. So these solutions that happen with differential equations, the x's or critical points that make our function f of x equal to 0, are called equilibrium solutions. And there are three types of these critical points. There's one called a stable critical point. So on either side of this point, the solutions converge to the critical point value. There are unstable solutions. So on either side of this critical point, the solution diverges away from that value. Or they're called semi-stable. So you can come in from the left and it'll converge to that critical point, but on the right-hand side it diverges away. Or if you can come in on the right, it could converge on the critical point, but on the left-hand side it diverges away. So we're going to... Alright, so let's solve problem 1 as an example. So we have our differential equation here. The first derivative is equal to x minus 4. And so the first thing we want to do is find the critical point. So we set the derivative equal to 0. And that tells us that our critical point has to be 4. And so now I'm going to make what's called a phase portrait diagram. It's basically a number line. So I mark 4, and then I want to check the value of the derivative at to the left and to the right of this critical point. So if I check it to the left, say if I put 3 in here, the derivative is going to be negative. So our function has to be decreasing. The slope is negative. And then if I check it to the right, say at 5, I put 5 in here, I get positive values, so our slope is increasing. And at this critical point, you can see it's going away from 4. And this is what we call an unstable equilibrium. So we can plot a direction field. You can see a constant solution right here at x equals 4. But if I put in any other initial condition, that if it's above 4, you can see the solution curves all go away. And if it's below 4, you can see they all diverge away also. So this is what happens with these types. So we can solve this differential equation. It's easily separable. We've solved a lot of them. And this would give us, this is the solution we would have. And it definitely looks like it's an exponential function. So depending on what value of t we put in here, you get different value, you get different solutions. So let's do another example. Let's do problem 4. Here we have this differential equation. I want to find its critical point, so I set the derivative equal to 0, and I solve for them. So we can factor this twice, and this is going to give us 2 different solutions. So the derivative of 0 is when x equals 2 and x equals minus 2. So now we have 2 critical points, one at minus 2 and one at 2. And so again, I'm going to check different areas of this graph and evaluate the derivative at that point. So if I take a number to the left of minus 2, say minus 3, I put it in here. I'm going to get a minus value here. I'm going to get a minus value here. I have 2 minuses, so I get a plus value. So the function has to be increasing. Let's take a value right here in between minus 2 and 2. Let's try 0. If I put a 0 in here, I get minus 2. I put a 0 in here, I get plus 2. I got a minus 2 by a plus 2. That gives me a negative value. So the slope is decreasing. And all this whole region is decreasing. And so you can see that right now you can see the critical point that everything's converging to minus 2. And now I'm going to look at a spot that's greater than 2 over here. We've put 3 in here. This is positive. This is positive. Two positive numbers are a positive number. And so the slope is increasing right here. So here we have two critical points. The point 2 is considered unstable. If we've seen that before. At minus 2, it is stable if it converges to that value. And then we can solve this differential equation. It's a separable differential equation. Also, we have methods of solving it. We can solve it. And then if we plot the direction field, you can see our constant line solutions of 2 and minus 2 at our critical points. And you can see if we choose any initial condition that's greater than 2, it diverges away. You choose initial conditions between 2 and minus 2. It converges to minus 2 here. And if you choose an initial condition that's less than minus 2, down in this range, it all converges towards minus 2. Let's do one more example. Let's try this one. So here's our differential equation. So here we want to find our roots, and we have three possible roots, except they're all going to be repeated. And again, they can be minus 2 and 2. Any of those values. So we're going to do the same thing we did before up at the two critical points at minus 2 and 2, and we're going to check to the left of minus 2. So that's a minus 3. So I put a minus 3 in here. It gives me a positive 9. So these are all positive. So now the slope is positive. So let's check in here in 0. So that's 0. So this is negative, negative, and negative. So three negative numbers give me a negative number. And so the slope is decreasing there. And then if I put in a value of 2, or greater than 2, say, let's say 3, this would be positive, positive, and positive, and so it should be a positive number. And then again, we get unstable at 2, we get stable at 2, and then we can plot the direction field, and you can see how it's going at the constant lines at 2 and minus 2. Any solution starting out greater than 2 goes away from 2. Any solution starting out in between 2 and minus 2 goes towards minus 2. And any solution starting out below minus 3 goes towards minus 2. Let's try one more example. Let's try this one. So let's find the critical points. Set the derivative equal to 0. We're going to find three critical points, plus 2, minus 2, and 0. So now we have three critical points we have to deal with, and we're going to evaluate our phase diagram the same way. At minus 3, this would be positive, this would be positive, so and then this whole thing would be positive. And so we get a positive increasing slope, so it would be going towards minus 2. If we're going to be in here, say minus 1, positive. Now, minus 1, this is positive, but it's less than 4, so this would be negative. So we have a negative and a positive, so we're going to get a negative value. And then we're looking over here between 0 and 2. Let's try 1. So that's positive. This is positive, but that's less than 4. So this will be negative, so this will give us a negative value. And then we'll try out here a greater than 2, say 3. So positive, positive. This whole expression would be positive, so it would be a positive value, it would be increasing away. And we get our critical points again. So at 2, it's again unstable. At minus 2, it is stable again. But at 0, it's semi-stable. You see how it converges towards 0 if you're in between numbers of 2 and 0, but diverges away from 0 if it's numbers between 0 and minus 2. So here is our solution curve again. Numbers greater than 2, it diverges away. Numbers between 2 and 0, it converges to 0. Numbers between 0 and minus 2, it goes towards minus 2. And numbers below minus 2, it goes converges towards minus 2. Okay, so a topic that shows up when dealing with stability of equations, I should say the stability of solutions to these differential equations, is a topic called bifurcation. Now, basically what bifurcation is that the number of critical points change based on the conditions of the problem, and this usually shows up in a logistic problem with harvesting. So you're trying to predict the population of, say, fish that would be in a lake, but there's a certain amount of fish that would be harvested throughout the whole time period. So here, let's show an example. Here is a logistic equation right here. You got some population x times 10 minus x, where 10 is the carrying capacity of this population, but I'm removing a set population h every time period. Okay, so if we find the critical points of this system, we set the differential equation equal to 0, and then I get this quadratic equation here that I can solve for its roots, and I get these roots. Well, depending on what h is, these roots can change, right? So I could make h 25, and then I'd have 5 for a solution, right? But let's say I made h, instead of 25, 26, then I get a negative number here, and I have an imaginary number, and that causes problems. Or I could make, say, h1, oh, sorry about that, let's make it a perfect square. Let's make h9, and then this would give me 16. The square root of 16 is plus or minus 4. I should say we have two solutions here, the addition and the subtraction. So if h was 9, then this would be 16. So I'd have a 1 here and a 9 for a solution. So how do we analyze systems like this? Well, what we do is I want to rewrite my solution this way, where c is my critical point, or x. Okay, basically I'm trying to solve this. I'm moving the 5 over to my x of t here, where that's my critical point, squaring and getting this under. So what I want to do is make a graph of this. Okay, so here's a graph. So basically I'm graphing over different values of c. I'm changing c and h at the same time and making a graph. And this gives me this parabola type shape. So I'm going to, h goes from minus 10 to out here 30, and my c's are going from, it looks like minus values all the way up to maybe 10, 11, and I'm plotting these points as it comes out. So let's look at this. Now, let's say I have a solution right here, okay? That only happens when, let's see, I could make this equal to h, say 25, that gives me a 0, and then c would be equal to 5, that would give me a 0, right? Alright, so I only have, this is what they call a bifurcation point. That's where things, basically we have one critical point at this time, and then I could look at this h value down here, maybe that's somewhere around 9 or 8, and it looks like I have 2 critical points here, right? One here and one here. So I went from 1 and I went from 2 depending on my harvest model. And then I could come all the way over here and say h is greater than 25, something like that, right? And I have no critical points, right? 0 critical points. So this is what bifurcation means. Depending on the harvest that I choose, I can have different critical points.